Hello, welcome to this video on mercury. So in this video we'll be exploring why mercury is a liquid at room temperature. Now mercury has had a fascinating history. It was known to the ancient Egyptians, to the ancient Romans. It was then used in traditional medicine and used a lot in alchemy. And its properties was mysterious even after we developed a fairly sophisticated quantum model of the atom based upon Schrodinger's equation. And in this video we're going to be seeing why we need relativity to actually explain particularly the incredibly low melting point of mercury. I think mercury melts at about minus 39 degrees Celsius, so that means even when you have solid ice, you have a liquid metal. And bearing in mind mercury is a metal, transition metal, I mean that's really weird. Very, very weird indeed. And we'll be seeing why relativity explains mercury's very low melting point. So mercury is so mysterious, I thought before we go into a bit of maths and bring in relativity, it'd be helpful to talk in a little more detail about how mercury was so mysterious for so many cultures. Now, the symbol for mercury in the periodic table is Hg, which stands for something like hydrogyros or something similar to that. And it translates as liquid silver. You know, I mean, if you're interested in alchemy, you might have heard of mercury being referred to as quicksilver. So the idea of mercury flowing is very, well, goes back a fair way. But originally, when we found mercury, we found it in compounds. So one particular compound known to the ancient Egyptians and ancient Romans was a red kind of dye or paste used in the decoration of Egyptian tombs and even in ancient Roman cosmetics. Now I think the common name for mercury sulfide at the time was canonite, and it was one of the many kind of compounds that were used for colouring in ancient Rome. Ancient Romans also used to dye some of their tunics purple using iodine or iodine compounds. So yeah, the cosmetic place was probably the healthiest or filled with the most healthiest chemicals. But mercury had a use. And if we look back early in medicine, mercury was believed, probably partly due to its special properties, to be fairly powerful. So it was used in skin treatments, it was even used as an antidiuretic. And the alchemists, looking at mercury and probably seeing the way it flowed and maybe even the way it seemed to dissolve other metals. When you put mercury in contact with at least some of the metals like aluminium, it seems to swallow up the aluminium or slowly dissolve it. That's not quite what's happening, but from a visual perspective it looks very similar. And in alchemy, mercury was believed to contain the kind of essence of a metal and therefore was very important in transmutation, turning one metal into another. I mean, yeah, one of the main goals of the alchemist was to be able to turn base metals into gold. Now they didn't succeed in this, but it's worth saying they made many compounds and interesting chemicals. So, alchemy as a science wasn't particularly useful, but alchemy as a kind of technology did prove to have uses, even though they never quite managed to turn base metal into gold. Now, one might think that after the Bohr model of the atom, where we began to look at the quantum mechanics of the atom, particularly how electrons are distributed in energy levels, and then we refined that model with Schrodinger's equation to take account of things like subshells and orbitals, and the idea that electrons don't really orbit the nucleus of an atom at all. One might think that, after that development, we would have a fairly solid idea of how electrons act around atoms, and therefore the chemical properties of different elements, including mercury. Now, it's worth saying certain chemical features of mercury were explained by considering the different shapes of the shells, which subshells are filled, which are not. So Schrodinger's equation does go a long way in certain respects to explaining the properties of mercury, but it really didn't explain very well why mercury was a liquid at room temperature. It particularly struggled to describe why mercury remained a liquid until, fairly significantly below 0 degrees Celsius. So it was clear that there was a piece of the puzzle missing. But it's worth saying that quantum mechanics and relativity developed around the same time. So people did suspect, even from the 1970s, that relativity might actually have the answer. And it turns out relativity does. And we'll be exploring the relativistic effect on the mercury atom, and how that relates to mercury's low melting point in this next and last bit of this video. So, to take account of the relativistic effect on a mercury atom, I'm briefly going to go to the Bohr model of the atom, and then explain how relativity can alter it. Now, it's worth saying, if you want to look at the relativistic effects on an atom rigorously, you need to look at relativistic corrections to the Schrodinger equation, or go full on and look at exact calculations involving the Dirac equation. But to try to make this video as accessible as possible, I'm going to be looking at relativistic corrections to the Bohr model of the atom, and the Bohr model is kind of a crude quantum mechanical model where it takes account of the idea that the energy levels of electrons in an atom are quantized, but it doesn't really look at subshells or things like that. So in the Bohr model of the atom, electrons kind of act like standing waves. And when you take the idea that electrons act as standing waves and have to form standing waves, with the equation for the de Broglie wavelength of the electron. So the de Broglie wavelength describes how big, if you like, the electron wave is. When you put the de Broglie wavelength of an electron along with the idea that electrons form standing waves, and it kind of makes sense that electrons would form standing waves because standing waves are are in principle stable. At least they don't naturally decay unless there is energy import or loss from a system. When we put these two equations together, we end up with this equation on the screen. So this equation is saying that the angular momentum of the electron well, I should say orbital angular momentum. I'm not including spin here because for that we would have to make use of Dirac's equation, so I'm just sticking with orbital angular momentum, not intrinsic angular momentum. So the orbital angular momentum of the electron L is quantized in units of h bar. The idea of it being quantized relates to electrons from standing waves, and the idea of it being quantized in units of h bar relates to the de Broglie wavelength for the electron. Now, the angular momentum is defined to be mass times velocity times radius. So if we look at the classical picture first, and by classical I mean I am ignoring relativistic effects, we would say that the rest mass of the electron times its velocity times its classically expected radius would be equal to n times h bar, where n tells me the energy level of the electron. And if we rearrange the equation, we get that the classical radius would be, and we can write it in various ways, but it would be nh bar over the rest mass times velocity, or equivalently it would be nh bar over the momentum, but the classical momentum, so where we're taking the mass of the electron to be the rest mass. Now, the important thing to note here is that as we make the electron heavier, the radius drops. Now, classically, and for the purposes of this video, by classically I mean ignoring relativity, so classically the electron's mass is just a constant. There's no way to change that. It's not in any way a dynamic variable. It's just a fixed thing of nature. But when we bring relativity, although the rest mass of the electron is fixed, the key thing is the rest mass only refers to the apparent mass of the electron when it is at rest or nearly at rest. However, when it is moving quickly relative to us, particularly when it is moving close to the speed of light, its effective mass, its relativistic mass, is significantly different from its rest mass. So if we bring relativity, we replace the classical momentum with the relativistic momentum, and that means we replace m0v with gamma m0v, where gamma is the Lorentz factor. Now, if you would like to learn more about the Lorentz factor and why we multiply the rest mass by the Lorentz factor to get the effective mass of the electron, I would recommend watching my video on Einstein's equation equals mc squared, and how we can generalize that to talk about mass more generally, or equivalently my video on full momentum, where I go into detail about the difference between relativistic mass and rest mass. I'll put links to those videos in the description, but yeah, if you prefer for this video, you can just take it for granted that the relativistic mass is equal to the Lorentz factor times the rest mass. Now, the Lorentz factor stays pretty much very close to 1 when the velocity is, let's say below 10% of the speed of light. I say, let's say, because whether the Lorentz factor being above 1 is significant depends on exactly what you're calculating and exactly in how much detail you care about the calculation. However, for a mercury atom, because it has so many protons, I think a mercury atom has something like 80 protons. There's a huge electrostatic potential keeping the electrons bound to the atom, and that means that the inner electrons in mercury, those in the first S subshell, are actually moving a significant fraction of the speed of light, about 50%. And in that case, the Lorentz factor does significantly divert from the value of 1. And that causes the relativistic mass of the electron to be significantly more than the rest mass, which means that the quantum mechanical relativistic radius of the electrons in the S subshell, the quantum mechanical relativistic radius of the orbit or the motion of the electrons in the first S subshell, that radius is a lot smaller than the non-relativistic counterpart, because as you increase mass, the radius shrinks. And if we compare our two equations, we can clearly see that the relativistic radius divided by the classical radius is 1 over gamma. And gamma is always greater than or equal to 1, and when you get up to significant fractions of the speed of light, gamma deviates significantly from 1 with no kind of upper limit. That is, gamma approaches infinity as the speed of a particle approaches the speed of light, and that's partly why particles with less mass can't travel at or faster than the speed of light. So going back to the idea that the speed of the electron is about 50% of the speed of light, and one can get that from a kind of more full relativistic treatment of the mercury atom. So taking into account, for example, Dirac's equation, one ends up with our equations. If you put in the speed the electrons are moving at is about 50% of the speed of light, you get that the radius of the first subshell, the first S subshell in a mercury atom, is about 85% of what we would expect it to be classically. So in other words, due to relativity, the radius of the first S subshell is 15% smaller than what we would expect classically. Now you might think, well, okay, that only applies to the first S subshell, and I'm using the S subshell because the S subshell is spherical, so these calculations work a lot better with Bohr's model than other subshells. However, because the energy levels of an atom are essentially they are mutually exclusive, or using the language of quantum mechanics, they are orthogonal, it turns out that the rest of the subshells have to also shrink by a similar amount. So the whole mercury atom actually shrinks and is about 85% of the size we would expect if it wasn't for relativity. And because the atom is smaller, the actual force holding the electrons to the atom is stronger. Because the force is an electrostatic force which obeys the inverse square law, so as the radius of the atom gets smaller, the force gets bigger. And it turns out the relativistic force is about 140% of the classical force, so nearly 50% more than what we would expect if we ignored relativity. So, in summary, the mercury atom is significantly smaller than we would expect if we ignore relativity, and because it's smaller, the mercury atom holds on to its electrons much more tightly. And that means that mercury is really bad at bonding as one would expect a usual metal to bond. And actually, mercury, in terms of bonding, is a lot more similar to a gas. I mean, mercury, because it doesn't really share its electrons or distribute them, because mercury atoms hold on to the electrons they have, the only way they can really bond, at least with each other, is through very weak van der Waals forces, the kind of forces that hold gas molecules together. Now, if you think of it like, although a lot of gas molecules are, well, gases at room temperature, you might wonder, well, why is mercury then a liquid at room temperature, not a gas? Well, mercury is very heavy, but importantly, as well as being very heavy, mercury has, each atom of mercury has a lot of electrons. And when you have a lot of electrons, you get fairly strong van der Waals forces, at least for van der Waals forces. And therefore, mercury is a liquid at room temperature rather than a gas. So essentially, mercury is a liquid and not a solid, because it doesn't take part in metallic bonding, because it holds on to its electrons, outer electrons, due to this relativistic contraction of the atom. However, mercury is still a liquid and not a gas, because mercury has a very large number of electrons, so has very strong van der Waals forces, at least as far as van der Waals forces go. So that's a brief kind of summary of why mercury is a liquid at room temperature. Now, as I mentioned, the idea that mercury was a liquid at room temperature thanks to relativity was around since the 1970s. I mean, before that, it was shown that relativity does have effects on transition metals, like the reason gold has the colour of gold is actually thanks to relativity. In that case, it's due to how relativity changes the spacing between the energy levels. So mercury's case, in terms of the relativistic effect, is a little different. But it was known, even in the 1960s, that relativity does have a role to play in the chemistry of atoms. But it took a while to show that relativity conclusively was responsible for the liquid state of mercury at room temperature, and it was actually shown by computer simulations. So, more and more, computing is becoming an important part of science. Biologists are using it to model proteins and how proteins fold and all of that stuff. And in physics, we can use it to model fairly complicated systems like the mercury atom. And the mercury atom is fairly complicated because there's lots of electrons, but there are also therefore lots of subshells and interactions between subshells to take account of. In this video I've just tried to skim the surface, but one could probably do a whole PhD on the relativistic effects on transition metal atoms. But anyway, that's kind of everything for this video. This video was a little bit shorter, definitely, than some of my other videos. If you've enjoyed it, consider liking or letting me know in the comments what you've enjoyed about this video, and if there's anything else you would like me to cover. So there should be more videos coming up in special relativity soon. I really want to get the playlist on special relativity finished over the summer, but I wish you a wonderful time till hopefully I see you again from the next video. I hope you enjoy the sun as well. Maybe bring a physics book with you to have a bit of a break and sit down Remember to drink plenty of hot water in the sea too, and wish you awesome time ahead. So keep exploring, and I look forward to sharing the wonders of the universe with you again soon.